So this is basically what is happening in an example over here where we have an input image and we are actually sliding a kernel, a 3x3 kernel, and we are getting an output feature map. So the input feature map here is just has a 1. We will be calling sometimes this depth channel, and the output feature map has again 1 channel over here. And what we have here is we have a couple of things that we need to introduce as terms in convolutional operations that we are actually doing inside the convolutional neural networks. So the first is the form of the concept of padding. And typically we are padding the input feature maps in order to do 2 things. We're achieving 2 things. Probably you have noticed that in an earlier kind of discussion where we had the operation of cross-correlation operation in this kind of image over here, the output feature map was always smaller in terms of spatial dimensions compared to the input feature map. And it is evidently so because the only way that this output feature map can be exactly the same size as the input is when the kernel is 1 by 1. So when the kernel has a spatial extent of 1 by 1, then we have exactly that situation. But in most cases where the kernel won't be 1 by 1, we will expect these output feature maps to shrink in terms of spatial content. And we do not want them to shrink too much because sooner or later we will be running out of spatial dimensions in our outputs, and therefore we cannot really go deep to construct deep architectures in these networks. So what we expect to do, what we have done, is we have, with padding, we are trying to manage this spatial extent reduction on one hand. As you can see, if we had this padding over here, then the output feature map is going to be much larger than otherwise. So if you can imagine it without a padding, then this sort of output feature map would actually be, I can't really sort of tell you exactly the dimensions, but if you see the sort of, if you do it visually, then you can actually see it's going to be probably something like a 3x3 output. Now the sort of another advantage of padding is that we allow the kernel to actually move into locations which would not be able to move otherwise. So a kernel, as we discussed a bit earlier, contains some values, and we would like all of the pixels, including the edge pixels of the input feature map, to be able to be correlated with all of the other pixels of the pixels of the kernel, and therefore padding allows us to do so. Otherwise, you can imagine this red kernel over here will actually only be able to correlate with those 3 pixels of the input feature map. Now this pixel over here can be correlated with both this pixel of the kernel and that pixel of the and this pixel of the sort of kernel that we have. So we have the ability to sort of get more information, especially towards the edges of that input feature map with padding. Another parameter that we should also sort of understand is this kind of stride. So stride is just like the stride that as you walk. This here actually refers to the number of pixels that you are skipping over in order for you to be able to do the next correlation. So here you see 2 locations of that kernel. In that location and the blue location, the red location, the blue location, if your stride was 1, then the blue kernel would have been right here. And while with a stride of 2, then we don't get one correlation operation for every pixel of the input feature map. And this is obviously is helping us to manage the complexity of these filters, and in fact goes slightly to the opposite direction of what we have said earlier, in a sense that in some instances we prefer to get for some of the layers of the convolutional neuron the stride parameter to be larger than 1. Typically the stride parameters of height and width are going to be the same, so that's what you see over here. The bottom line is that all of these parameters and far more that are to follow are hyperparameters, and we are going to be optimizing them for using hyperparameter optimization in order for us to define the complete architecture of a CNN. So here you see some animations that kind of reinforce what we have just quoted. Without padding, the kernel, the output feature map is going to be potentially significantly reduced in terms of spatial extent, something that will make any subsequent cross correlation with kernels not very useful. With padding, we avoid that, and here we actually have padding, combinations of padding and stride. So I suggest that you study this kind of animations to just get the gist as to what padding and stride are actually offering to us. But now the time has come to look at the operation of the convolutional neural network, and in fact describe, if you like, the single convolutional kind of layer in detail. We will start drawing a snapshot of a CNN layer operation that will actually help us to understand the general case where we have input and output feature maps coming into the CNN layer, but however these input and output feature maps possess different depths, and this is another parameter that we have to understand, that we are responsible for designing these layers with that the depth of what we will produce is our responsibility to design. So let's right now draw, if you like, a picture of that CNN layer in operation. Okay, let me call it the snapshot. We will see just a single snapshot of that layer, and this will also help us understand the what is the convolutional neuron. We already have seen the sort of sigmoidal kind of neuron. Now we will see in the fully connected dense layer architectures. Now we'll see the convolutional neuron in front of us. So the snapshot, let me call it snapshot of a CNN layer operation. All right, so let's draw now the general case as we discussed, that we have an input volume this input volume is associated with the output feature map of an earlier layer. Let's call that layer L-1. This is basically the feature map that was generated by the previous layer in general, and will have a depth of capital M L-1. It will have some kind of width. Let me make sure that you can actually see the whole pad here. This is W L-1, and the height over here would actually be okay, so this was a depth, and the height over here will actually be H L-1. All right, so that's basically the dimensions of my incoming volume, and this incoming volume has some kind of resolution in terms of number of height and width pixels. Let me just draw them quickly, because we would like to now draw the what will be the output out of this operation, which is the output feature map. Now the output is going to be generated at this specific moment in time. I have in general a filter that has 3x3 spatial extent. It is located, let's say, here at this moment in time, because that's why we call it a snapshot. And it has some depth. I want to discuss a little bit the depth, what makes sense for this depth of the filter to be. But when it is located over here, for sure, I'm expecting to have some output feature map. This output feature map will be probably smaller in terms of spatial extent. That's why I'm kind of drawing it like this. It has some kind of a number of pixels. Okay, and we'll have some kind of a depth. And this depth is definitely something that I need to control because it's one of my main design parameters. I'll be calling this depth ML. And evidently we have a different HL and WL dimensions. And this is basically my, volumes, input and output volumes. In general, I'm going to have input and output volumes. So the question I actually have right now is to understand a little bit about the depth of the filter. And we have three options. Either the depth of the filter will actually be deeper than the input feature map, shallower than the input feature map, or exactly the same depth as the input feature map. So let's try to do some kind of reasoning over here. Does it make any sense for the filter to be deeper than the input feature map? And if you think about it, the answer is no, it does not really make a lot of sense, because at the end of the day, we are going to be correlating the contents of that filter with the contents of the input feature map. And if the filter is actually deeper, then we are not going to be picking up anything from the input feature map, because we are going to, so why have it deeper? Okay, so, there's no point of doing so. If it is shallower than the input feature map, also it does not really make a lot of sense, because we are going to leave content that the input feature map contains for us on the table. So, the only reasonable assumption is this filter to be exactly the same in terms of the input feature map depth, right? In terms of this, depth of the input feature map. So it's just basically draw it as such. And in fact, it is really this filter that is going to be the one that we are going to be using to do this kind of a three-dimensional kind of a correlation over here. Now, to understand the contents of that correlation is kind of important, and what is actually even more important to understand what it will generate. As we will see shortly, what it will not generate the whole volume over here, but it will actually generate only one slice out of that output volume. Okay, to understand that kind of important point, let's do the following. Let me take so for that specific snapshot that I'm actually right now, I'm generating the specific, let me draw that like there, some specific result, which is a scalar, therefore it's a result of a single pixel, from this column, which is located at the coordinate I, j. So spatially wise, and I hope you remember what we have seen earlier in the sort of example architecture, in the CNN architecture diagram, let me just show you that kind of diagram again. For that specific snapshot, let's say the blue snapshot, I'm actually generating this scalar result. And using just one kernel, a filter of depth 1 in this case. So as it actually turns out, that filter at that specific snapshot, it will do a three-dimensional correlation and it will still generate a single scalar for me. Okay, and that single scalar will be at a specific depth. Okay, and the spatial coordinates of that scalar is I comma j, that the one I just drew. Now we will call that depth with an index in a moment, but what I want to do here is to just draw the complete column of pixels at the I comma j location. Let me just rotate them, this column, 90 degrees and write it over here. It will be evidently, this dimension will be ml, the depth dimension, and this is the because we are correspond to the earth layer. And let me just do exactly the same thing with the filter. So I'm actually taking the filter and decomposing it over here to the 3x3 kernels that it contains. And so these are going to be my 3x3 kernels. And this will be of dimension ml minus 1. So just took the filter, rotated 90 degrees and just decompose into its kernels. This is the L minus 1 layer. And so since I'm going to be generating a scalar, let's assume that I'm generating right now at that specific snapshot this is the I comma j coordinate. This is the column that corresponds to the earth layer and the I comma j coordinate. Let's assume that I'm generating this scalar over here. This scalar is going to be represented by the letter z. And we'll have evidently I comma j as the spatial coordinates. And we'll have a depth coordinate, which I will designate with the letter KL. And evidently 1 is less than or equal to KL is less than or equal to ML. And this will actually be the values that the KL index, which is the depth index, can take. And I will actually be using also a corresponding index to address each one of those kernels, which are going to be used for the determining that kind of scalar z. So that scalar z is going to be produced by using all of the kernels of the filter. And I am going to also need to define two other indices. The first index is going to be u, and the other index is going to be v, and these indices will actually be used to as spatial coordinates of the kernel. Okay, so my equation is the following. So given I comma j comma kl, given in other words the coordinates of the scalar which I want to generate, my scalar z, I comma j comma kl, are going to be given by three summations. The first two summations I have seen already in the plain two-dimensional correlation operation, the one that we just did in earlier. So this is u, summation over u and v. Definitely I'm expecting the spatial content of that kind of filter to be correlated and therefore dot product, to take the dot product with the contents of the input image. Okay, so this is the two summations over here. But also I'm expecting to now do a three-dimensional correlation operation. That's a third summation over an index I'll be calling KL minus 1. And this index addresses the specific kernel which I'm going to be using. So KL minus 1 is definitely the less than or equal to 1 and less than or equal to ML minus 1 in a similar way as we have seen earlier. So what is this kind of a correlation? It will be X of I plus U, J plus V, comma, KL minus 1, times W, where W now are the contents of the kernel, that now has U comma V comma KL comma KL minus 1. All right, so we have, in fact, the W is not the contents of the kernel. The contents of the kernel, yes, we can call them W, but W, I would associate W with this line over here, that for specifying this line, and have the U comma V coordinates, spatial coordinates of the kernel. That specific kernel, however, is provided by this index, is identified by this index. So this specific kernel is by this index. And the scalar it is going to be generating is located at the KL depth. That's why I need this W of Q comma V comma KL comma KL minus 1. Okay, so this will actually be the weights that are going to be, so a 4-dimensional tensor is being used here for specifying those parameters that we are storing those in those filters. And in fact, we only have one filter right now, so a 4-dimensional tensor to identify the parameters that we have used in this specific dot product over here. This is a 3-dimensional dot product, and as you can imagine, as I'm sliding the filter to another location in the next snapshot, the only thing actually is changing is the spatial coordinate that is being produced in this scalar. So the only thing, so by moving the filter around, I'm changing the I comma j of what I'm producing. Therefore, what I'm actually going to be producing is a slice, a specific slice out of this sort of output feature map. So the specific slice I'm just drawing over here, just one of the ML slices. So ML slices generates the complete volume. So this slice is the one that I am going to be generating, this complete slice, or effectively a matrix. And so from one filter, I'll be generating a single matrix, and therefore, and this is the important conclusion, from we need multiple filters to generate the output feature map volume. So for a volume, for the whole thing, for the output feature map, we need to be creating multiple filters. In fact, this thing over here is really the connectivity diagram of the convolutional neuron, what we call a convolutional neuron. A single filter is, and the operation actually we see over here is the operation of the convolutional neuron. And this is all of these parameters that we have used over here, the contents, if you like, of the filter, are the so-called trainable parameters. And we will now see an animation of this thing in our course site. So if I go to my course site and actually scroll down a little bit, then you can see now the 3-dimensional. So first of all, before we see the animation, we can actually see it's exactly the diagram I just drew, a bit different. I have an input volume, which is the blue over here, with has a depth d in. Definitely, as we mentioned, the input, the filter that we're going to be using has the same depth d in as the input volume. Doesn't make sense otherwise. And then in terms of the output volume, a single filter is going to be generating one slice out of the d out slices. So on one slice, let's say this specific matrix over here where my mouse pointer is. That is going to be what is going to be produced by a single filter. And this dotted line here indicates that if you want to generate the complete output volume with depth d out, you need d out of these filters. You need d out of these orange cubes in order for you to be able to generate a complete green output feature map. So I think it's worth spending some time in this animation. In this animation, you can actually see exactly what I just discussed. Here in this example, I have an input feature map of depth 3, and I have an output feature map of depth 2. Let's assume that that is the sort of a design parameter which I want to implement. Therefore, if I have an output feature map of 2, I need 2 filters. And these are the 2 filters. This is the filter W0 and this is the filter W1. And evidently, each of these filters has of depth 3, because 3 is also the depth of the input feature map. And at every specific snapshot, let's assume this is the snapshot that I just drew on a piece of paper. This filter is located at this specific location in my input feature map, and it is responsible for creating this scalar z, which is 9 in this case. Okay, so if I may, and as far as the output feature map is concerned, this filter is only able to plot, if you like, to determine this specific slice of the output feature map. Okay. If I want to continue, then we will see that the second filter is the one which is involved in the creation of the second slice of the output feature. So this is really the essence of a three-dimensional convolution. I suggest that you spend some time on this animation trying to understand what is going on, and you can toggle the movement just to be able to replicate the output scalar from the input values which have been provided over here. Talking a bit on this presentation of the snapshot operation of a layer, the site over here is quoting some kind of important formulas regarding the size, the spatial dimensions of the output feature map. I think it's important to note them down, so it is the floor of the height of the input feature map plus 2 times the padding size minus the kernel size divided by the stride size and plus 1. Okay, so this is the formula that will that you can actually use to understand exactly what will be your output feature maps are in terms of spatial dimensions, and of course this will be the input feature map sizes for the layer that follows. Okay, so what will actually be those layers? I think it's it's quite important to get into the discussion now about other architectural features before we go into some kind of a discussion about the advantages of convolution layers as compared to fully connected layers, which I think is best demonstrated using an example. Before we go into that example, let's look at another operation that we'll be calling the max pooling layer, or in general pooling layer, which is actually described here and is best demonstrated with this kind of image. In this case, what we see, we have an input feature map that has a depth of 1 in this case, and we do still have the concept of, if you like, of a kernel that we slide around just like in the convolutional layer, but in this case, instead of a nonlinear function like a ReLU that we have actually also seen in the fully connected layers, that we are still going to see in the convolutional layer, as we will see in that example, we will have another function. Let's call that function, in this specific case, it's shown as the max function, where the idea behind this is that we are going to not form a correlation result over here, like a dot product, but we're going to select the maximum element of what we see in the input feature map. Typically, we apply that function for each of the channels of the input feature map, but in some instances, we may apply it also across the depth dimension. What we are achieving is, evidently, we are achieving some reduction in the spatial dimensions of the output feature map, and that kind of intuitively understood as trying to select the most important features of the input feature map and transfer them out into the layer above for further processing. Okay, so that is the max pooling layer in this case, which is typically interleaved with convolutional layers, as we'll see in some example architectures. Closing, I want to emphasize another kind of specific parameterization of the convolutional layer that we call here the one-by-one convolutional layer. And it is definitely sort of a layer that it is being met in various kind of architectures. And maybe it does not really make a lot of sense to you the moment you see this kind of animation over here. Why on earth we're going to do one-by-one convolutions? Since as we discussed, we're trying to detect features, and typically the kernel sizes have larger dimensions than one-by-one. But I think the explanation potentially could be more intuitively understood if we see the three-dimensional version of this one-by-one convolution. So we have see here the orange filter that evidently the kernel size is one-by-one. And we have, as we discussed earlier, depth D that matches the depth of the input feature map. And as we also discussed earlier, this filter operation will move around. We're sliding around this filter, and we're creating one slice for this filter. So in this one-by-one convolution, we have just one slice. And as you can see, what we are achieving here, we are forming a scalar by combining the depth, compressing the whole depth dimension. So we actually have, we are seeing typically this type of layers, let's say towards the end of a network, the top of the network, where we just before the head, where we want to just summarize everything we have done and we have learned in terms of convolutions, operations, and across all depth dimensions that we have decided to do. And then we just need to compress that information to a matrix, and potentially that kind of slice is going to be flattened in order to be passed over into the head, which may consist of fully connected layers, as we'll see that in a moment. Okay, so that's one application of the one-by-one convolution operation. All right, so it kind of looks like a multi-layer perceptron or a dense layer, as it is combining these depth dimensions into that scalar. All right, so let's now see some example architectures. These example architectures could potentially be like the toy network that we see here, where we have, as we discussed, a convolutional layer followed by nonlinearity and max pooling layers. And finally, at the end, we expect to see a fully connected layer that is going to play the role of the head of the network, where we have, let's say in this case, 5 classes that we would like to do a classification on. But instead of looking at this toy network, I think it's a bit more instructive to look at, I would call it canonical architecture, called VGG, from the initials of the authors of that kind of architecture. This architecture is, I would call it an architecture that I suggest students to start from every time they want to look at these convolutional networks, because they do represent some kind of initial good architecture that we can sort of make some conclusions regarding the dimensionality and the patterns that we expect to see in a typical CNN architecture. Instead of looking, if you like, in the most modern versions of CNNs, I think it's worthwhile looking at this to understand a couple of things. So the first thing that we'd like to capture over here is this image and understand what is really happening. Okay, so the image is, in this figure we see a CNN layer, so a CNN network that consists of multiple layers. And one striking thing from the get-go that you can see is that the CNN is, the dimensionality of the CNN is, in terms of spatial dimensions, is evidently shrinking as we are going deeper. So we see the convolutional layers followed by max pooling layers, and then towards the end we see the fully connected network, which is the head. So in terms of spatial dimensions, we are actually decreasing the spatial dimensions because evidently we are using kernels which are larger than 1 by 1, but at the same time, what we are also seeing is we see an increase in the depth dimension. So in terms of numbers over here, 224 by 224 pixels are the spatial dimensions of the input images, and then we have 64 to be the depth dimension of the, or equivalent, the number of neurons in the that we have in, or the number of filters that we have in that layer. So this is also our responsibility. So our responsibility are twofold. One is to, with the padding and stride parameters, to massage these kind of spatial dimensions we need, and at the same time also select the number of filters. How many convolutional neurons are we going to engage in that layer? So as you can see, we go from 64, 128, 256, 512. That is really the end game with respect to number of filters. The intuition behind the increase in the number of filters as the network becomes deeper and deeper is the following. The network is learning more and more complicated features as we are going deeper. The first layers are learning representations which are simple shapes. I will call it similar things that you would expect to for you to understand when you look at, if you like, at a kind of a primitive shape like a circle, a triangle, or whatever have you. And the subsequent kind of layers are actually learning more and more complicated representations. We'll see in a moment some examples of exactly what these layers are learning, and via suitable visualizations. So as you are trying to create combinations of these simpler representations, you probably ought to be doing more of those combinations as you go deeper, because you are trying to understand whether or not there's one combination that actually magically generating the right set of representations in subsequent deeper layers, such that your head can actually do the job. So that's the first intuition regarding the increasing the depth of the filters. The second is that you can afford to. I mean, you can afford having that kind of increase in the depth of the filter, and without really paying too much complexity in the terms of number of operations, because your spatial dimensions of the feature maps which are produced from earlier operations are shrinking. So you increase the number of filter parameters, and still you're not really paying any complexity sort of penalty because of that. Okay, so these are the two things that we can actually mention about this kind of architecture that looks again like a pyramid, but this pyramid is a kind of works in a different way as compared to what we have seen in fully connected architectures. And now I think it's worthwhile spending some time on an example, and this example is a Python notebook. This example is actually shown over here. You can actually click on this and open it in Colab for execution. However, the notebook in your case over here will actually be working as it is. So in the next video, we'll go through this example and then see exactly what's going on in terms of and the API and the implementation of a CNN.